All right, strap in everyone, because today we're diving headfirst into the world of physics.
Always exciting.
It is, especially with the notes you sent over. Center of mass, momentum, and collisions. I have a feeling things are about to get pretty wild.
You're not wrong. These concepts are way more important than people realize. I mean, they're basically the foundation for how we understand motion. Everything from, like, the smallest particles to the entire universe.
No kidding. Well, let's start simple then. Center of mass. In my notes, it's defined as the point where an object's mass is perfectly balanced. So, like, am I thinking about this right if I imagine a seesaw?
You're actually spot on with that. Think about it. If you and a friend are on a seesaw, to balance perfectly, you have to move around, right? Based on your weights. Well, that center of mass is that exact point where the seesaw would be totally balanced.
So it's kind of like the balancing point for an object, but
Yeah.
instead of people on a seesaw, it's like all the teeny tiny bits of mass that make up the object.
Bingo! And here's where it gets a little crazy. The center of mass doesn't even have to be inside the object. Like, take a donut, for instance. Where would you say its center of mass is?
Well, in the middle,
Yeah.
where the hole is. But there's no actual donut there.
See? That's what's so cool about it. It's like we can treat the entire donut as if all its mass were concentrated at that one single point in the center, even if it's empty space.
That's pretty wild when you think about it. Okay, but how does this whole balancing point thing work with, like, really complicated shapes? Or even, like, a group of objects?
Good question. It's the same basic idea, but the math gets a bit trickier. Imagine, like, a system of stars, like a binary star system. You know, where two stars are orbiting each other?
Yeah, I can picture that.
Okay, so their center of mass isn't actually in either star, it's somewhere in between. Closer to the star that's more massive, of course.
So like a weighted average then,
Right.
where the heavier parts kind of pull more and where that center of mass is located.
You got it. And this whole concept, it's super important for understanding, well, pretty much how anything moves and interacts. But let's take it a step further. Think about the motion of the center of mass.
Okay, so now we're not just talking about a balancing point. We're talking about how this point actually moves around in space.
Exactly. And here's a key idea to wrap your head around. That center of mass, it moves as if all the mass were concentrated at that point, and as if all the forces were acting directly on it.
Okay. Do you have a real-world example? I'm having a little trouble visualizing that.
No problem. Picture a figure skater, right? Doing a spin with their arms tucked in. Even though their arms and legs are moving all over the place, their center of mass is following this smooth path. Makes sense, right?
Because gravity is the only thing acting on it, pulling down on that single point.
Exactly, you're getting it. Now, let's switch gears a bit and talk about momentum. In my notes, it says it's the quantity of motion, which is, a little vague, but basically it's calculated by multiplying an object's mass by its velocity.
So a heavy object moving really fast has more momentum than a light object moving slowly. It's like the difference between a runaway train and, I don't know, a bicycle.
Perfect example. Momentum is all about how much oomph something has, how hard it would be to stop it. Like that runaway train, it's got a lot of momentum because of its mass and speed.
Okay, so then like a tiny bullet, even though it weighs way less than a train, it could still have a ton of momentum if it's moving crazy fast, right?
Absolutely. And that leads us perfectly into another big idea, impulse.
Okay, late on it, what's impulse?
Impulse is basically the change in momentum that happens because of a force acting over a certain amount of time.
So picture a golfer hitting a golf ball. The club, for a split second, is applying a huge force to that little ball that's causing a massive change in the ball's momentum and sends it flying.
Perfect example. Or think of a car slamming into a wall. Oof. The force of the impact only lasts for a super short time, right? But it causes a huge change in the car's momentum, bringing it from like 60 to 0 in an instant.
Okay, I'm starting to see how all this ties together. Momentum is like the object's motion, and impulse is what changes that motion. It feels like we're building up to something really big here.
You can sense it, can't you? It's time to talk about one of the most fundamental laws in all of physics, the law of conservation of linear momentum.
Ooh, that sounds serious.
It is. It basically states that in a closed system, where there aren't any outside forces messing things up, the total momentum of the entire system will always stay the same.
Wait, really? So even if things are like bumping into each other inside the system, the overall momentum doesn't change?
Nope. It just gets redistributed. Think of a firework exploding in midair.
Ooh, good example. All those sparks are flying out in every direction.
Right, but before they were all packed together in the rocket.
Right.
So before it explodes, that rocket has a certain amount of momentum. After the explosion, all those little pieces are moving in different directions, and they all have different speeds too. But when you add up all their momentums, it still equals the initial momentum of that rocket. Wild, right?
So it's like a cosmic balance sheet where momentum is the currency.
Yeah.
You can't create it or destroy it. You can only move it around.
Exactly. It's a pretty elegant idea when you think about it. And it's true no matter how chaotic things get. Billiard balls smashing into each other, a rocket launching into space, even a figure skater flinging their arms out during a spin, the total momentum always stays the same.
Mind officially blown.
Yeah.
I'm starting to see momentum everywhere I look.
Okay.
I gotta ask, are all collisions created equal? My notes mention something called elastic and inelastic collisions.
Ah, you're right. That's a big distinction. It all comes down to whether kinetic energy, the energy of motion, is conserved or not during the collision. A perfectly elastic collision is one where all the kinetic energy stays the same.
So like imagine the most perfectly bouncy ball bouncing off the most perfectly hard surface. The energy just keeps getting transferred back and forth, right? It bounces forever.
That's the idea. Of course, in the real world, it's never perfectly elastic. There's always a little energy lost to, like, friction and stuff like that. But the point is that in a perfectly elastic collision, the total kinetic energy before and after are equal.
Okay, that makes sense. So what about inelastic collisions then? My notes say that those are collisions where kinetic energy isn't conserved.
Right. In an inelastic collision, some of that kinetic energy gets transformed into other forms of energy. Things like heat or sound. Just picture two cars colliding and crunching together. A ton of that kinetic energy is going into the sound of the crash and all that heat from the metal bending.
So you're saying that the energy isn't really lost, it's just changed into different forms.
Exactly. Energy can never be created or destroyed. It just gets transformed.
Ah, that makes way more sense. So in an inelastic collision, the objects could end up moving slower or even stop completely because some of that motion energy got turned into, like, sound energy.
You got it. And then there's a special case called a perfectly inelastic collision. That's where the objects, after they hit, they just stick together. Like if you threw a lump of clay at a wall. Splat.
So they basically become one object with their masses combined and then their final velocity. It all depends on that conservation of momentum thing we were talking about.
You're a natural at this. You're totally seeing how all these concepts are connected. Now, I know you're probably wondering how we actually measure how bouncy a collision is.
You know me too well. Hold that thought, though, because we've covered a ton of ground already. I think it's time to give our listeners a moment to catch their breath and process all this amazing physics. We'll be back soon to dive even deeper into the world of collisions and beyond.
Welcome back. Ready for round 2.
Absolutely. And I'm dying to know more about measuring that bounciness we were talking about. It's not like we can just grab a ruler, right?
Not quite. We use something called the coefficient of restitution, or E for short. Basically, it's a number, goes from 0 to 1, and it tells us how much of that kinetic energy is kept during a collision.
Okay, so a 1 means a perfectly bouncy collision like those we were picturing, where no energy is lost. And 0 means they just completely stick together.
You got it. Think of dropping like a tennis ball and a super bouncy ball, same height. The super bouncy ball is going to bounce way higher, right?
For sure.
That's because it has a higher coefficient of restitution. More of its kinetic energy is conserved, so it rebounds with more energy.
Oh, okay, that's a really good way to picture it. So like a car crash, that would have a coefficient of restitution closer to 0, but a billiard ball bouncing off a bumper, that'd be closer to 1.
You're on fire today. The coefficient of restitution, it's basically our way to measure that bounciness. And it's actually really important in a lot of real-world stuff, like designing car bumpers, so they absorb more energy and make crashes safer.
This is so fascinating. Okay, so we've talked a lot about collisions, but I'm thinking back to something you said earlier about the center of mass. You said it makes it easier to analyze complex systems. But what about those systems where, like, the mass is changing?
Ah, you're talking about variable mass systems, like rockets.
Bingo. Because they're burning fuel and losing mass as they launch, but they still accelerate. How does that work if momentum's supposed to be conserved?
That is such a good question. It all boils down to the momentum of the exhaust gases that are shooting out the back. So even though the rocket itself is getting lighter, the total momentum of the whole system, that includes the rocket and those gases, it all stays the same.
Wait, so even though the rocket's losing mass, Its momentum stays the same. That doesn't make sense.
I know, it's a little counterintuitive, but think about it. Those gases are being shot out the back at an incredible speed, and they're carrying momentum with them,
Yeah.
the opposite direction of the rocket.
So it's like trading mass for velocity,
Yeah.
but the total momentum stays balanced.
Nailed it. It's a perfect illustration of how this conservation of momentum thing plays out in a real-world scenario. And it's exactly how rockets can reach those incredible speeds, even in space, where there's nothing to push against.
I'm starting to see how this seemingly simple law of conservation of momentum is actually incredibly powerful. I mean, it's governing everything from like tiny collisions to rockets flying through space. But I gotta admit, I'm still kind of fuzzy on how that thrust force is actually created in a rocket. Can you break that down a bit more for me?
Sure. Imagine you're standing on a skateboard and you chuck a heavy ball forward. What happens?
I'd roll backwards, of course.
Exactly. Conservation of momentum in action. To keep things balanced, you and the skateboard, you move back with the same amount of momentum as the ball, just in the opposite direction.
So the rocket engine is basically doing the same thing, but it's like a continuous stream of really hot, really fast gas molecules shooting out the back. That creates the thrust force that pushes the rocket forward.
Precisely. And the faster and heavier those gas molecules are, the more powerful that thrust force is.
This is making so much more sense now. Okay, so we've mostly talked about collisions that happen in a straight line. But what about when things collide at an angle?
Ooh, good question. Things definitely get more interesting when we start talking about two-dimensional collisions. Because now, instead of just thinking about momentum in one direction, we have to think about both the momentum in the direction of the crash and the momentum that's perpendicular to it.
So like we're analyzing two separate collisions at the same time.
That's one way to think about it. Imagine two billiard balls hitting each other on a pool table. They almost never hit head-on. They usually glance off each other at weird angles, right?
Yeah, totally.
So to analyze that, we have to consider both the forward momentum that causes them to, move apart, and also the sideways momentum.
Okay, I see. And this kind of analysis, it's used for way more than just pool, right?
Absolutely. Think about accident reconstruction, particle physics, even understanding how planets and stars move. It's everywhere. But there's one more type of collision we haven't really talked about yet. What happens when objects hit at an angle, but they stick together?
Oh, like a car accident where the cars get all tangled up.
Perfect example. Those are called oblique collisions. And unlike elastic collisions where things are bouncing off each other, in these cases, kinetic energy isn't conserved. Some of it gets turned into other stuff like heat and sound, even just the energy it takes to crumple the metal.
So how do we even begin to analyze these real-world collisions where things aren't bouncing neatly?
Don't worry, conservation of momentum still comes to the rescue. We just look at the total momentum of everything before the crash and after the crash. And because the objects are stuck together, we treat them as one big mass after the collision.
So even in those messy real-world crashes, we can figure out the final velocity of the whole combined mess just by looking at the momentum of each object before they hit.
That's the beauty of it. Conservation of momentum is super powerful. It helps us make sense of all kinds of interactions, from the super simple to the super complex.
My brain is officially overflowing with physics. We've gone from the center of mass to rocket science and all sorts of crazy collisions.
It's been quite the journey, right? And we're not done yet. Let's take a quick breather, and then we'll come back and uncover even more cool stuff from the world of physics.
Okay, we're back. And I'm still trying to wrap my head around all that collision stuff. It's amazing how much physics can explain about, well, pretty much everything around us.
You said it. And we're not even close to done. I mean, there's a whole universe of amazing stuff out there.
Before we get too carried away, is there anything else we should touch on? Any last mind-blowing moments for our listeners?
We talked a lot about how momentum is conserved, right? But it's important to remember momentum isn't just some number, it's a vector.
Right. It has both magnitude and direction.
Exactly. So it's not enough to just say, oh, momentum is conserved. We have to make sure it's conserved in every direction.
Oh, okay, I see. So that's why when we're analyzing collisions, like especially in 2 or 3 dimensions, we have to break those momentum vectors down into their components. It sounds complicated, but I guess the basic idea is still the same. The total momentum before has to equal the total momentum after, and we got to factor in direction too.
That's it. You're getting it.
Okay, good. I have one last question that's been bugging me. We talked about rockets launching into space as like the perfect example of conservation of momentum. The rocket loses mass as it shoots out all those gases, but the total momentum of the system stays the same.
Yeah.
But what about those gases? They're just, like, floating out there in space, right? What happens to their momentum?
Great question. And it brings up a really important point about momentum. It's relative,
Meaning?
meaning the momentum of an object. It depends on your perspective.
Oh, okay. So, like, from the rocket's perspective, those gases have a ton of backward momentum, right? But for someone watching from, say, a space station, it might look totally different.
Exactly. The person on the space station, they might see those gases moving really slowly
Yeah.
or even not moving at all. It all depends on their relative velocities.
Wow. That is so trippy. So the universe has its own kind of built-in relativity, even for something as basic as momentum.
It does. That's why it's so crucial to be super clear about your frame of reference when you're talking about momentum, or any physics concept, really.
Well, I think my brain is officially full. What an incredible deep dive this has been. Center of mass, momentum, impulse, that super important law of conservation of momentum. We even touched on relativity.
It was quite the journey.
It really was. And a huge thank you to you for guiding us through all of it. It's been a blast.
The pleasure was all mine.
And to all our amazing listeners, thanks for joining us on this wild ride through the world of physics. I hope you've all gained a new appreciation for how beautiful and powerful physics is. It really is the science that helps us understand the entire universe. So until next time, keep those questions coming, stay curious, and never stop exploring.